Hey everyone, welcome to this explainer. I know exactly why you're tuning in today. You're staring down Unit 3 of Pathophysiology, and let's be real, it is notoriously intimidating. We're talking respiratory mechanics, fluids, electrolytes, and the ultimate beast, acid-base balance. But hey, do not panic. Today, we're taking this absolute mountain of information and turning it into a fun, interactive guide. Think of this as your ultimate Patho Playbook. Because by the end of this explainer, you aren't just going to memorize these concepts, you're going to truly understand them.
Here is our game plan for today. Level 1 covers the lungs, specifically obstructive versus restrictive disorders. Level 2 navigates fluids and electrolytes. Level 3 cracks acid-base homeostasis. And finally, we end with the boss battle, an interactive case study.
All right, let's dive right in. Level 1, the Great Airway Divide.
So this right here is our anatomical battlefield. Notice the trachea and the major bronchi branching out. This upper section, it forms the conducting portion of our airway. I want you to think of this as the highway. It's strictly for the passage of gases, kind of warming and filtering the air as it goes. But absolutely no gas exchange happens here. The real magic, the actual gas exchange, only begins deep down in the respiratory portion, specifically in those respiratory bronchioles and the alveoli. And when disease strikes, it attacks these specific zones in very, very different ways.
Okay, I want you to pause for a second and think about the physical mechanics of breathing. On one side, we have obstructive disorders. The fundamental issue here, increased resistance to airflow. The patient can breathe in just fine, but they can't get the air out. It literally gets trapped inside. On the flip side, we've got restrictive disorders. Here, the problem is decreased lung expansion. The lungs or the chest wall become incredibly stiff, so the patient simply can't get enough air in. So remember, obstructive is an out problem. Restrictive is an in problem. Keep that hard line in your mind as we move forward.
Let's look a bit closer at the obstructive side by contrasting the two heavyweights of COPD. Emphysema, classically called the pink puffer, physically destroys the alveolar walls and elastic tissue. The airways literally collapse during expiration because they've lost that radial traction, that physical outward pull that normally keeps them open. Contrast this with chronic bronchitis, or the blue bloater. Here, the airway is physically blocked by inflammation and massive mucus hypersecretion, leading to this chronic, really productive cough. So one destroys the actual tissue structure while the other suffocates it with bronchial plugs.
Now, moving over to diffuse interstitial lung disease. In this condition, an unknown antigen triggers an immune reaction that actually attacks the alveolar epithelial cells. And as a result, fibroblasts just start proliferating, dumping massive amounts of collagen directly into the interstitium. That once spongy, healthy lung, it becomes thickened, fibrotic, and incredibly stiff. In end-stage disease, it actually turns into this rigid, honeycomb-like structure.
Before we leave the lungs behind, we absolutely have to talk about a critical, acute restrictive condition, ARDS. Acute respiratory distress syndrome is typically triggered by a massive systemic insult. Think severe trauma or sepsis. This causes widespread damage to the alveolar capillary membrane. The capillaries get super leaky, leading to non-cardiogenic pulmonary edema. Surfactant levels drop, meaning the alveoli just collapse, which is a condition called atelectasis. But the most crucial takeaway here, because that membrane is so severely damaged and filled with fluid, simply throwing more oxygen at the patient doesn't solve the hypoxemia. The oxygen literally cannot cross that damaged barrier.
Moving right along to level 2, fluid and electrolyte balance.
I want you to imagine what physically happens to a cell when you add way too much salt to the extracellular fluid. This is hypernatremia. Water always wants to balance things out by moving to the area of higher osmolarity. So, when the vascular fluid becomes highly concentrated with sodium, it acts like a giant magnet, pulling water straight out of the surrounding cells. The result? The cells literally shrivel up like raisins. And this is exactly why severe hypernatremia causes such profound neurological dysfunction.
Now, let's test your real-time clinical reasoning a bit. We know fluid moves back and forth all the time. But what happens when the physical pressure inside the capillary, the hydrostatic pressure, pushes outward against the vessel walls too hard? Think about it for a second. Where does all that fluid actually go?
Well, that fluid is forced directly into the interstitial compartment, creating edema. Edema happens when that delicate balance of pressures just completely breaks down. You can have increased capillary hydrostatic pressure pushing fluid out, or decreased capillary osmotic pressure, like a lack of albumin, failing to pull fluid back in. You could also have a blockage in lymphatic drainage, which traps the fluid, or just overall sodium and water retention expanding the volume everywhere. To maintain this crazy delicate volume balance, our body relies on two ultimate volume controllers. First up is ADH, antidiuretic hormone. I want you to think of ADH strictly as the tap water hormone. It tells your kidneys to retain pure water, which dilutes your body fluids when osmolarity gets a bit too high. Second, we have aldosterone. This is your saltwater hormone. When blood volume or blood pressure drops, aldosterone tells the kidneys to retain sodium, and water naturally follows that sodium. This expands the overall extracellular fluid volume. Tap water versus salt water. Remember that, and honestly, you will never confuse the two again.
All right, take a deep breath. Welcome to Level 3, Cracking Acid-Base Homeostasis.
Let's start right off with the golden rule. Blood pH must be maintained in a razor-thin margin, specifically between 7.35 and 7.45. Now, any solution with a pH less than 7 is technically acidic in chemistry, sure, but in human physiology, dropping below 7.35 is clinical acidosis. Conversely, rising above 7.45 is alkalosis. Your body works tirelessly, 24/7, to stay right in this tight range. But why does that matter? Why is the body so incredibly obsessive about this 7.35 to 7.45 window? Well, here is the absolutely crucial point. At extremes of pH, specifically dropping below 7.3 or rising above 7.5, proteins physically begin to lose their function. And if your cellular proteins stop working, your vital organs stop working. Keeping this balance isn't just about passing a patho test, it is quite literally a matter of life or death. To prevent catastrophic organ failure, your body has this amazing tag team compensation system. The lungs are your rapid response team. They can adjust your breathing in literally minutes to excrete or retain carbonic acid, which is a volatile acid, just by blowing off CO2. But they can only handle carbonic acid. The kidneys, on the other hand, are the slow, heavy lifters. They take days to reach full effectiveness, but they can excrete any other acid in the body by pumping out hydrogen ions, and they can generate and retain bicarbonate to buffer the blood. So it's fast and specific versus slow and comprehensive.
All right, it's time for the Boss Battle, our interactive acid-based case study. Let's put this into practice.
We're going to look at a set of lab values. Our goal here is to determine if the primary culprit of the imbalance is respiratory in nature or metabolic in nature, and whether it's acidosis or alkalosis. Get ready to analyze.
Here is the ultimate test. Your patient's blood gas comes back with these numbers: a blood pH of 7.14, a PCO2 of 55, and a bicarbonate or HCO3 of 27. Look closely at those numbers. What exactly is going on with this patient?
Let's see how this builds deductively, step by step. Step 1. You always look at the pH first. It's 7.14, which is well below our normal 7.35. Therefore, we know immediately we are in a state of acidosis. Step 2. Look at the PCO2. Normal is generally 35 to 45. This one is 55. That is abnormally high, meaning there is an excess of acid in the blood. Step 3. Connect the dots. The high CO2 perfectly explains that low pH. And since CO2 is controlled by the lungs, the primary issue has to be respiratory.
And there's our verdict: respiratory acidosis. The primary issue is a massive excess of carbonic acid because of impaired ventilation. The lungs are just failing to blow off the CO2. It's a perfect callback to our restrictive and obstructive pulmonary disorders from level 1, right? Things like emphysema or a blocked airway cause this exact inadequate exhalation. Clinically, this patient might show tachycardia, a headache, maybe lethargy. To survive this, those heavy-lifting kidneys will have to kick in to compensate by retaining more bicarbonate.
Which leads me to leave you with one final provocative question. As this patient's kidneys start their slow compensation process over the next few days, attempting to fix that dangerously low pH, what exactly will happen to that bicarbonate level of 27? Is it going to go up or is it going to go down? Think about what the body actually needs to neutralize that acid. Lock in your answer, trust the structured logic you've built today, and you are absolutely going to crush your patho exam. Thanks for joining me on this explainer. Keep learning, and I'll see you next time.